good morning, good afternoon, good evening, everyone. We need an all-purpose phrase, I think, to greet everyone because there are so many potential time zones that people could be in. My name is Vinton Cerf. I'm Vice President and Chief Internet Evangelist at Google and one of the Turing Award winners. I'd like to ask each of my colleagues to introduce themselves so that all of you can know who to blame for commentary. Let's start with, Avi, would you like to start?
Sure, yeah. My name is Avi Wigderson. I work at the Institute for Advanced Study in Princeton. My main work is in the theory of computation, computational complexity, algorithms, randomness, and related areas. The Institute for Advanced Study, for those who don't know, is a research institute in Princeton where we don't have students, we have only postdocs. And so it's a cool place.
It is a very cool place, quite right. Alessio, how about introducing yourself, please?
Yeah, so thank you. I'm a mathematician. I work on, let's say, analysis, partial differential equations, and I'm a professor at ETH Zurich, although as probably as you can guess from my accent, I'm Italian. And I do have students, actually, I was lecturing this morning. We don't have the the same condition as in the institute, but so I teach, mathematicians and engineering at ETH. Nice to meet you.
So welcome to the show. Yann, would you like to introduce yourself, please? Yann, are you hearing us? Oh, maybe not. Yoshua, maybe you should introduce yourself first.
Sure. So my name is Yoshua Bengio, and I'm a computer scientist, professor at the University of Montreal, and a scientific director of Mila that I founded a few years ago. It's a large machine learning institute with academics from Montreal, with about 600 grad students. And my work mostly has been around deep learning. Yann and I and Jeff Hinton have received the Turing Award for our contributions to pioneering this field.
So, Yann, are you able to hear us? It looks like we need some technical help there. So I hope that the team in the background can contact Yann and help him. In the meantime, the topic here is computing and
Hello? We lost Vit. Yes. And I see that Yann now hears us. Maybe Yann, you can introduce yourself.
Yeah, can you guys hear me?
Yes.
So please go ahead.
Okay. So I'm Yann LeCun, and I'm a professor at NYU, and I'm chief AI scientist at Facebook.
So the topic of today's discussion is advances in computing and mathematics. And I think I'd like to start out with the artificial intelligence side of things, simply because it's so much in the news these days. So I'm interested to know a bit more about how Yann and Yoshua see the current state of affairs. A lot of people are quite worried about artificial intelligence. They speak of it as potentially dangerous. And yet you work with this dangerous substance every day. Can you say a little bit more about your sense of safety for the rest of us, for example? Is this really scary technology? Is this technology that we can rely upon? So how do you deal with the concerns that people express? So Yoshua, let me start with you.
Sure. So first of all, there is not like a huge danger right now, although there are uses of AI that are concerning and that require government intervention. For example, I've been very much involved in trying to call governments to the international level to ban the use of AI in lethal autonomous weapons, like killer drones. And there's a lot of discussions about regulating the use of AI in places where human dignity is at stake, discrimination can happen. So there are good reasons why we need to be concerned. Now, in the longer term, that's where I'm most concerned, because you asked about like what are, is there something that prevents me from like being feeling good? Yeah, we're building very powerful technology, and it's true of AI, it's true of other technologies. Like I'm scared of what we'll be doing with biotechnology, for example. These technologies could be extremely useful for us if we do the right things with them, but they can also be used in ways that can be destructive and dangerous for even the survival of our species, right? So it's not for tomorrow, but I think we need to realize that we don't have the right, say, social structure, social norms to cope with the power of the things we're gradually building into our hands and the hands of anybody, including crazy people who could use these things.
So these wise words are exactly the reason that we have these kinds of conversations, because people like you thinking hard about these technologies can inform us about what norms would be appropriate. So Yann, let me turn to you. You're free to respond to the scary part, but I'm actually interested to see whether you have something to say about the advantages of where we are and where we're going with these machine learning technologies.
Well, the advantages, the use of AI today are mostly beneficial, not everywhere, but you have things like automatic emergency braking system for cars now that are deployed pretty much standard in every car, at least in Europe. Those things reduce collisions by 40%. So they save pedestrians from being run over. They do all kinds of stuff. So that's good. It saves lives. There is a huge amount of research and trials, not a lot of deployment yet of AI for medicine, obviously, particularly for imaging. And that, again, is going to get generalized. A lot of AI used today for advancing science and medicine, particularly sort of biology, but even things like material science and things like that. There's a lot of hope, for example, that sort of deep learning-based phenomenological models of chemical reactions could help design things like catalysts that could help, with climate
capture carbon.
For example, carbon capture is one of them.
Or batteries.
Another one, which some of my colleagues are working on, is in fact a collaborative open project called Open Catalyst. Is the idea of trying to find catalysts that would make the separation of hydrogen from oxygen efficient. Because if you could do this, then you could store energy. So you could, cover half of the Sahara with solar cells and just, produce hydrogen and basically power the planet with, zero carbon emission. So large-scale energy storage is a problem. Perhaps deep learning could help with this, right? There's already kind of work also in material science and to kind of explain phenomena that we observe for which we don't have reductionist theory. So those are the good sides. Another good side, which is probably the biggest use of machine learning today, is content understanding, content management, content filtering, and this is good for a lot of people because we're submerged with information, and we need help in sort of filtering the information that we actually see. And Facebook, of course, is sort of at the front end of this. So is Google and various other companies, and it's an unknown territory. So it's fraught with potential dangers that Facebook is very well aware of. Facebook is being attacked for ignoring those issues, but they're not ignoring this issue at all. I can tell you that's one reason why Facebook is investing so much in Google, in AI, and Google is doing the same, right? So because it's so important, and in fact, when we deploy systems like this at large scale, we realize that there are side effects that we didn't predict, or that there are people who are trying to exploit the system for their own purpose, and in the process, kind of doing bad things to society. So it's going to be kind of a progress of realizing how we can use this, those technologies for the better. Now, the dangers, I think, the things that people are afraid of, they probably should not be afraid of. So there is the first thing that people are worried about is is AI going to invade my privacy? And the answer to this, so first of all, this has nothing to do with AI. It has to do with just the availability of data. And the protection against this is the strength of our democratic institutions. So, it doesn't work in authoritarian governments, unfortunately. So they use AI to spy on their people, right? So that's a bad use of technology. So, my name is associated with convolutional nets. Those are used at a large scale by the Chinese government to, basically discriminate its own population and do face recognition at a large scale. Not necessarily a good thing.
I'm sorry to interrupt. I'm concerned about time, and so I wonder if we could shift. First of all, thank you, because that gives us a sense of sort of the extremes here and why these are such powerful tools. We need to pay attention to them. But speaking of powerful tools, I wonder if Avi and Alessio could speak to another aspect of computing. And we keep hearing the term computational X for many different values of X, whether it's linguistics or biology or astrophysics or something else. What should we anticipate now that we are able to apply computers to so many different disciplines? Does that fall into either of your sphere of interest and expertise, the notion of applying computers to what would normally be sort of wet laboratory things, this notion of using computers in lieu of physical experiments? And if that's not an area of particular interest for you, feel free to shift the conversation to something that you're more excited about. But either of you, Avi or Alessio, can you speak to that question?
Avi, you want to start?
Yes, please.
I can.
Yes, please, go ahead. Alessio,
okay, I can start. Yeah, okay, sorry. Well, in my case, I think, it's not something very related to my research. What I do is most really on the theoretical side, but one thing which is interesting is the impact of computers in general on mathematical research. So more and more, more and more. Before it was really unusual, but now you see computer assistant proofs in mathematics, which is something which, is not, it's really useful sometimes, right? I mean, maybe with the tool of mathematical skills, you can reduce a problem to a finite number of problem which would have maybe infinitely many cases to study, just a finite number of cases, and perhaps this number of cases is small enough that then you can just give it to a computer, and that can help to just rule out the remaining, still perhaps thousands of cases that you could not do by hand. But there is also another aspect which is interesting, which is this debate whether AI could really be used to solve problems. So in some sense, in general, computers now are able to to give mathematical proofs. They're able to solve exercises, mathematical exercises and stuff. So one could ask himself, okay, we will really need, for instance, mathematicians to do mathematics in the future, I don't know, 80 years from now? Or can you do a lot of stuff just with computers? And there are a lot of debates about this. I had chats with many people, and you see both sides of the medal. I think some people think that computers could really not take over, but really cover a big chunk of research, and others be less. I'm more of a, I don't think computers can really overcome and do what humans can do, but research is made of many steps, and then I think that computers could really take over in some of more standard mathematical proofs that become more routine over time, which on the one hand one could think that this is good. On the other hand, I think there is a risk in that, right? Because in reality, when you in any area, in any discipline, when you do research, you are able to do more and more advanced research also because you train yourself on more reasonable problems. So less, but then if the computer is able to solve them for you in no time, then it's very difficult for you to find the kind of motivation to say, okay, even if a computer could do it, I have to do it by myself because that's the only way to train myself on then something which will allow me to do more. So, I don't know, I'm thinking like a young PhD student who has to do some research at the beginning. Usually it's, it can be more basic. But then if the PhD student knows that he can just click a button and get the answer to his first PhD problem, you have to prevent the student to do that. So I don't think we are going to say we're going to see anything like that in less than 20 years. So I'm not super worried, even more. But I think it's something interesting to be careful about.
Well, let me. I would take away from those observations that algebraic processes, which can be more or less automated as long as the symbology and the manipulations are clear, could certainly make a computer a powerful tool to assist someone in pursuing a proof, for example. So, Avi, where are you on all of this? Do computers show up at all in the space of your mathematical research?
I would say that computation itself, the very notion of computation, of computational processes, is certainly in the back of my mind since I was an undergrad. My research is theoretical, and there's something about the way you phrase the question which I sort of rebel against, because you talk about the influence of computers and computing technology on mathematics, on science, on society, whereas there's huge amount of influence of theoretical ideas, of models. We are modeling science, of algorithms, of structural results about the complexity world, about randomness, about hardness, which leads to, let's say, a cryptographical scheme that everybody uses. There's plenty, and there's a lot of research in the theory of computation, which fits into mathematics and help both define new problems and resolve old problems. Are great collaborations with analysts, with geometers, with algebraists, and so on, where the very, the point of view, the computational point of view that we are trying to seek, not just, let's say, the existence of mathematical objects, but means to efficiently get into them, leads to new mathematics. The same computational lens fits into biology, into physics, and many other sciences, and even the social sciences we know, and I think that it enhances all these sciences and mathematics in great ways, even if computers did not exist. They also lead often to the generation of new technologies. I mean, cryptography, or even the very computer started from the brainchild of Turing, right? I mean, before that, we didn't have, and others at the time, right? There was first a theoretical model, and then technology followed. This is true about so many that we see and use, things we see and use. Many of the algorithms that we use, Fourier transform, signal processing wouldn't exist without it. There are many other examples. I mean, machine learning probably wouldn't exist as we know it if there was no way to compute gradients in linear time instead of the obvious quadratic time, right? I mean, and so on. So, I just want to stress that the theoretical framework, the theoretical ideas, the focus on efficiency in algorithms, the modeling of computer phenomena, these, create great synergy with the sciences and with mathematics and lead them forward.
So what this makes me think of is this wonderful ping pong effect between science and engineering. You have scientific ideas, and then in order to test them, you need to go build something. And once you build it, you either discover it works or it doesn't work. If it doesn't work, you have to figure out why. And if it does work, you use it to actually do something, which then informs theory. And these things are mutually reinforcing. So you, the four of you, are at the forefront of your fields. And I wonder if, remember, we have students who are very curious about what they should be doing. And so I'm interested to know what each of you is actually excited about in your fields that keeps you going, that makes you want to persist. So I'm going to come back to Yann again and ask what elevates you out of your chair about the fields of research that you're in the middle of.
Well, with all the success of AI in the last decade or so, we're still very far from having figured out how humans and animals learn. They seem to be learning much more efficiently than all the machines, all the techniques we've devised so far. So there is probably another paradigm of learning that we have not discovered, which is akin to the one that is used by biology. I think our best shot for this is the type of learning that babies or small animals do by computing models, learning models of the world by observing the world and by acting in it. So that's what I'm excited about. That's the first step. That might take us perhaps to a stage where AI has as much first has some level of common sense, maybe as much as a house cat or something like that. And then the second stage is trying to figure out how to make reasoning of the type that we know about in humans compatible with learning. We know how to do reasoning with logic, and that's incompatible with learning because it's discrete and combinatorial. And so the question is, how do we do reasoning in ways that are compatible, that are differentiable, essentially? So that's kind of the second thing. And if we can put all those things together into sort of an overall architecture, we might arrive at machines that have some level of common sense, that have autonomous behavior and things like that. And that will probably take decades. But that's really what I'm excited about. In the short term, it's called self-supervised learning. That's what I'm excited about. But you can hear.
This is very exciting to me because the idea of being able to learn something and common sense and learning leads to potentially curiosity, and of course that is very exciting. Children learn from small numbers of examples. I find this just astonishing because when we do machine learning today, you run millions of tests in order to teach something fairly simple. So Yoshua, what about you? What's causing you to pump energy into your work?
Well, at the high level, I'm completely aligned with the objectives that Yann set out and why they are important. I'm focusing more on the reasoning part these days that he mentioned. And there's a reason I want to mention. Besides the fact that humans reason and have cognitive processes that neuroscientists and cognitive scientists understand to some extent, but we don't know how to do similar things in computers. And of course, some of that has inspired classical AI, symbolic, rule-based AI. There's another reason why it's interesting to look at this, and it has to do with maybe something really practical and concrete with the limitations of current machine learning. Current machine learning is incredibly robust compared to what we had 10 years ago, 20 years ago, in any area of AI. But it's still much less robust than humans. So what I mean by robust here is that faced with a new setting, a new scenario, humans can quickly adapt. Like if you've been driving all your life in North America and then you end up in London, you're going to drive on the wrong side of the road. But it's painful, but you survive, and you actually, in a few hours, you learn to do a pretty good job. So what is going on there? So that's not something our current machine learning is able to do. And if you look at what's going on in people's brains, or you just ask them what's going on, is that they're paying attention. And there are things going on in their brain that is a bit different. That's akin to imagining what could happen. So like counterfactual reasoning and causality and planning and thinking about the rules here, the rules of the road. And that ability to reason, imagine, and so on makes it possible to very quickly adapt to new settings out of what we call out of distribution. A form of generalization that's more powerful than the classical IED form that we've been studying, mathematically. And in fact, this raises a lot of interesting mathematical questions. Like, what does it mean to generalize to a different distribution? I mean, you need to make some assumptions, otherwise there's no guarantee anything could work. But humans do it, so they're probably taking advantage of that are embedded somehow in our the way our brain works. And so this opens up all kinds of interesting connections between cognitive science, neuroscience, math, in statistics, and the study of causality, and the kinds of machine learning questions that Yann and I have been asking about representation. Like, how do we represent knowledge in a way that's going to make it easy for us to generalize to new setting? I think one way to think about reasoning is it's combining old pieces of knowledge in novel ways. And that's an ability that we're trying to put into deep learning. So it's very exciting because it could be a very different style of machine learning, of deep learning, that we could be building in the next decade. So I don't think this is going to be easily done in the next 6 months, but it could really be transformative.
So, as you speak, I immediately think of two words: abstraction and modeling.
Absolutely.
It's very powerful that we are able to look at something, experience something, and then build a kind of abstract model of it, then reason about it, and learn something from that.
Yeah.
Well,
and a big question is, how do we discover the abstractions? Because a lot of what has been done in the past is assume they're given. And the kinds of things that Yann and I, have been recognized for is how do machines learn high-level representations, which ideally are these high-level abstractions.
So speaking of abstractions, I have a feeling our two mathematicians are operating in those spaces. And I wonder, what is it that keeps you excited and interested? Avi, let's start with you.
There are plenty of things. I think that I'm blessed to be in a field that is extremely dynamic and full of bright young people, and so new ideas and new results and new solutions to all problems keep popping up, and that part is exciting on a daily basis. There are many fundamental reasons, like Yoshua and Yann talks about machine learning. These are, of course, fundamental questions, and probably deserve also mathematical understanding, like Yoshua described. For me, I mean, the most basic, still exciting after 40 years of failure, is why can't we prove that anything we want to compute is difficult? I mean, the experience we have in life is that almost any optimization problem we want to solve is hard, is exponentially hard. I mean, that's, and on the other hand, we cannot prove that any problem, any natural problem, requires more than linear time, more than reading the data. We don't know that multiplication is harder than addition. We somehow feel it, maybe because we were taught these algorithms in this order in second and third grade, but we don't know that. We don't know that Fourier transform cannot be done in linear time, and then, of course, if it did, then it would be even greater for technology. We don't know how to prove that a single problem is hard. So this, it's encoded into the previous MP question. But the abstraction of it is just why, is our inability to prove computational tasks are difficult. This is the most exciting problem for me. That's one I'm spending most time about. We can do this if the algorithms have a hand or two tied behind their back. So on restricted types of algorithms, we can prove limitations. But we have no way of knowing. We are great at assuming things. So the whole of cryptography is resting on the fact that some computational problems are difficult, but we don't know that. If we knew, if we could prove that factoring is difficult, maybe it isn't. But if it is, if we could prove it, it will be. You'll feel much better. That this type of questions, understanding why it is hard to prove that problems are hard, is for me the most exciting direction.
This is lovely because as you're talking, I'm thinking, sometimes there are problems that you're presented with, and they're presented in a particular form. And you discover that a change of variables produces a completely different representation of the problem. And suddenly the solution becomes obvious, but it wasn't obvious in the form that you saw it at first. And suddenly you discover, oh, this isn't as hard as I thought it was. So I can just imagine what a revelation it would be to discover that different ways of representing the problems leads to better answers. Well, maybe we can find something more now from Alessio about what is keeping you excited about your field.
Well, many things. So I switched. I won't say I switched, but I liked in mathematics to look at kind of different problems. From I started with very much in optimal transportation, which is originally a problem coming from economics. So what is the cheapest possible way of moving resources from one place to another? Then what excited me about this field is that it could be used for other areas of mathematics. So it could be used for to solve problem in geometry, to solve problem in PDEs, to solve problem in probability. It has become very fascinating. And then recently, actually, optimal transport has been started to be used also in machine learning. So this kind of optimal transport allows you to sometimes measure distance between objects. So you can decide to measure distance between images. You can use that perhaps then to do gradient flows. You can do gradient flows with optimal transport. You can do many things. So I was, I think, lucky to be in a field that is evolving so much, and also that is touching so many different areas. But also, I like to change. Like recently, I focus a lot on what is called phase transition problems. So problems where you try to understand how, for instance, ice melt inside water, which are questions that are super classical. They exist since more than 100 years. You can do a lot of modeling, but in reality, if you try to do to understand from a mathematical viewpoint really what the solution should do, they're very, very challenging because you need to develop a lot of new mathematics. So I think what I like about mathematics is that it's very rich. You can jump from very practical questions and get inspired by practical problems to these so classical questions that still have zero answer. And the beauty is also that sometimes just to try to answer this question, you can find new interesting mathematics. So it's like it's an interplay between pure and applied that goes on together. One inspires the other. So these have always been like this, but I think now also with these all advancements in, for instance, computer science, it's really a continuous source of both of inspiration, but also source of problems that really can touch from the more applied areas of mathematics to the more pure ones. So I don't know. I'm very excited to be, here now with so many things happening and having so much mathematics still to be done. At least in my area, it's very, very dynamic in this moment.
You know what this makes me think of? It makes me think of an intellectual holodeck. Mathematics allows you to it allows you to explore new ideas. You can invent new mathematical space as needed, and so you just keep going in this holodeck. Well, we have about 8 minutes left, and we do have some time for Q&A. But what I would like to ask each of you, if you could, briefly, if you were advising a student in your field, what would you tell them to look at now? And let me start with Yann.
Self-supervised learning, particularly for things like vision, learning from video, learning how the world works by observation. That's the big thing. How do we do that?
I love that. Yann, what about you? Or Yoshua, I'm sorry. What about you?
So I'm not going to repeat the thing I was excited about. Obviously, I would like more people to work on this because I think it's transformative. But one thing I'd like to add is machine learning can now be applied in many areas of what we call social good. Things like what Yann mentioned with the environment, but also in healthcare, education. And that's going to be very motivating for young people. And we need more people to be part of this movement. So I really encourage youngsters to look at those intersections between a domain of application where It could be very important for society, and maybe there's not enough industrial investment because it might not be yet profitable. But we need researchers to get into this to help us face the next pandemic or deal with climate change, for example.
These are all very practical, and I love the way you're all tying together the theoretical and the abstract to potential utility in the real world. Avi, if you were advising a student right now, where would you direct them to pay attention?
Yeah, well, I've been advising many students before I moved to the institute. So I was at the Hebrew University. So my experience is that it's extremely important to let students discover what they like and what they are good at. And for that, they need to experiment, to look at, some different areas, take a variety of courses, read a variety of papers on different topics and discover what their strength is. That's the value of a good undergraduation. And also during graduate school. There are lots of important problems in the world. I mean, there are no shortage of big problems that we would like to solve, from just food to everyone, and climate and so on. In my field, I think these problems I've talked about that I'm extremely excited about. I think that the sciences have not integrated into many theories the computational aspect, namely the fact that whatever process you study is in fact a computational informational processes, whether it happens in plants or in cells or in the galaxies and so on. And often theories do not integrate into them the fact that time has to elapse. I mean, the black hole firewall paradox, with many years in physics, seems to there's a way to get out of it if you just realize that it takes time for the radiation to leak from a black hole, and if you integrate this time, this may help resolve this paradox. It's just one example of many. So some of this is happening, but I think the very realization that natural processes are computational processes, and natural theories therefore should integrate the computational point of view into them is a great open area to get in.
I like very much your point about go find out what you're good at. There's no point in pursuing research if you're not good at it. So exposure to problems that you are that resonate with you and you have skill with seems like a good idea. And it doesn't identify any particular field. It just tells you what you should be doing based on your own personal experience. So Alessio, if you were advising the student at this point, what would you suggest that they do in your field?
Well, I think so. It's always a matter of. So one thing which is, I think students don't realize. So we were discussing about understanding what are the right skills, understand what you like. So it's very easy probably to identify what you like. I think it's not so easy to understand where the skills are, because it takes time. In fact, so it's not this research process. It's kind of involved, right? So the moment where you really understand that you're good at something, especially at least in mathematics, sometimes it takes many years, because there is a lot of training in reality that you have to do. There is a lot of, it's like, do you need to be a genius to do math? There are nice posts by Terry Tao that says that's not, right? Research is made of hard work. You spend a lot of time exercising and things. So the point in general that I try to convey, and is more general than just my field, is that frustration is just part of everyone's life, I think, once you do research. And I think it's thinking that you can just, if you have frustration, means you're not good, and then the people who are good is because they can just solve whatever they try to solve. I think it's a false statement. I mean, in reality, you just challenge yourself always with harder and harder problems, and there is always a usually the problems that you try to do are, you want to do them because you don't know how to solve them, and then that's why we're all in the same pot. We're all frustrated because we cannot do them, but then there is the satisfaction one time out of tens or hundreds times that the things don't work. So what I try to convey is that failure is not a problem. The point is to try what you like and do your best to reach the highest level you can reach, whatever it is, right? It's not good to say, this is my level, I already know what I can achieve. You don't know what you can achieve in life. If I thought that, if I had decided in the past that where was my level, I would never have done what I did, because I would never put the bar that high for myself. I would have put a very low bar. Instead, I just try to do every time the best, and then you try to do a bit better and better, and then you see where you reach. So I think the point is to follow passions. Then if you work already in mathematics, for instance, in optical transport, I think is or PDEs. One thing important I see in this moment is really, it's true that the academic world is becoming a bit more and more competitive because we have a lot of people, but in the end, I think that if you have a passion, you should persist and follow your dreams, because in the end, life comes back together, and even if it's a bit tough in the early years, things improve.
I think you put your finger on something that's driving all of us, and that's passion to know. I want to understand. Yep. I want to know, how does this work, and why does it work? Or if it doesn't work, why does it not work? Well, we're basically out of time. So let me thank all four of you for participating in this part of our discussion. I think we're going to go on now to talk to some students and see what questions they have for us. And I'm assuming that's going to be handled by the sixth person that's on the screen now. So I'll turn to you for help.
Thank you, Vint. Brief information, my name is Tarek Bezold. I used to be an academic, never like you guys, but at least I dabbled in it for a while. Now I'm doing AI safety in industry. Still, I'm here as the voice of the student, having been a participant in 2013 myself. And I'll fire right away. We have questions from, I'd call them questions of faith to very practical questions. And let's start with one of the questions of faith. Is computation a natural process or a tool among many for studying them?
Okay, who wants to take that one?
I can take it.
Go ahead.
Computation is a process. I think all processes we know essentially are processes which evolve by a sequence of simple, mostly local steps. It can be, in any, it can be man-made or, abstract or natural in any physical system. When we study it, it progresses slowly with operations that seem like they hardly do anything, and yet they can generate beautiful flowers and human beings and solar systems and all sorts of things. So I think that computation or the study of computation is the study of these kind of processes. This is the field. That's what defines the field. Dijkstra has a famous saying that computer science is about computers as much as astrophysics is about telescopes. So I think the understanding of computation is basically universal for understanding the world, understanding ourselves, understanding learning, understanding. That's my view.
It's a wonderful view. Anybody else want to jump in on that? Okay,
I need to agree.
Yes, this is the beauty of what Avi was saying, and of course Dijkstra's comment is that mathematics and computing are a lens through which we understand things. And there are means for maybe even making predictions about how things will unfold. Anyway, let's go to the next question.
Exactly. This also is, in a way, a methodology question. So, how to challenge the widespread belief that simply throwing more computing resources and data at a problem will produce important advances?
This sounds like a machine learning response. So yes, Yann.
I can answer that. There's many ways you can fail, and the best way to realize this will fail is you try and you fail. So, I mean, certainly we're not going to, the lofty goals that Yoshua and I were talking about earlier, getting machines to become truly more intelligent, this is not going to be attained by just scaling up the current techniques that we have. This is not because we're not blocked by the fact that our machines are not powerful enough or our data sets are too small. We're blocked by some conceptual thing that we haven't really discovered yet. So in that sense, scaling, getting more data, more computation is not going to solve that problem. Now, there's a lot of problems that can be solved by more computation and more data. And certainly if you can spend enough resources labeling a data set for whatever problem you want, and the data set is big enough, and you have a big enough computer with enough GPUs or TPUs or whatever it is that you're using, and a big enough neural net, it might work. I mean, most applications of machine learning today work this way, but we need to get out of this, and this is why I was advocating for self-supervised learning. We need to basically get machines to learn general knowledge about the world, okay, and then specialize them for a particular task, and that will require considerably less data than if you train the system from scratch with labeled data. So in fact, standard methods in natural language processing now all work this way. There's always a pre-training phase, which is completely generic, and then a kind of fine-tuning phase for getting the system to do what you want. It doesn't yet quite work for computer vision and other applications, but there's fast progress over the last year or so.
Let me add just one word. Can I add one word?
Please.
Yeah. So when the best algorithm you have for a problem requires exponential time, you can throw as much data and computing power at it, and you could only solve tiny cases. You have to improve the algorithm. I mean, otherwise you would never do it. And we have plenty of examples. We can solve linear systems in extremely fast because we have a good algorithm. If a system of quadratic equations, we have no idea how to do it in less than exponential time. And you can throw whatever, the whole world will be a computer, the whole universe will compute for you, and you won't solve an instance of size 1,000.
You know what, I as I'm listening to this, I keep thinking, when we try to do something, we think that, and it doesn't work, our first reaction is, that should have worked. Why didn't it work? It's kind of like cooking. Sometimes it doesn't work. And the thing that you learn most quickly about is stuff that doesn't work, and you find out why. Well, let's go to the next question.
So this one is in particular addressed to Joshua and Yann, but I think it goes to all of you. What are your views around recent interest in fair algorithms? What's the source of the problem? And then there's the comment, in my humble opinion, algorithms aren't unfair on their own.
I'll let Yann go.
It's a complex problem. I don't know, Yoshua, you want to go? I can
no, go ahead, Yann.
Okay.
Why would an algorithm or a machine learning algorithm, why would it be unfair for some value? Well, what does unfair mean? Now, that's another big issue.
Well, there are many possible reasons. One reason, which is the primary reason experimentally, if you look at everything that goes on in machine learning, is bias in the data. So there might be bias in the data because you don't have as many examples of one category as you have as another one. You can have correlations between variables, one of which is irrelevant to the problem, but because it's correlated, you get the wrong answer in the end. Here is a good example that's very famous. You train a system to recognize. This is an inconsequential one, but there are some that are much more consequential. You want to train a system to recognize images, and you have all kinds of images of cows, and the cows are only always on the sort of green background because there is grass underneath. all of a sudden you have a picture of a cow on the beach, and the system does not recognize the cow because it's used to seeing cows on a green background. So so there's all kinds of correlations like this. People are actually victim of that. So as when we learn about things, we are ourselves subject to biases in the data. These are causes of societal biases of people kind of react, picking the wrong features, if you want, to determine the category or the quality of something or someone. So that's the primary cause, but there are other causes. So there are certainly biases, statistical biases in the model. They don't usually translate into kind of societal biases. It's very hard to argue that, for example, logistic regression is biased towards certain answers rather than others that have societal consequences. But there are certainly biases, and people have been kind of studying this quite a lot. So there are many causes. It's very important to identify those before a system is deployed because this can harm people. Research in causal inference, for example, in identifying correlation that really are not causal, things like that, I think are probably kind of one of the most important areas there.
Let me strengthen just one thing that Yann said in passing, which is that fairness in algorithms is a problem not just with algorithms that are run on computers, but algorithms that are run in the brains of the judges, the bank loan officers, parole officers. The issue of fairness is not only in the realm of machines, and we have to understand, define, and sort of implement ways that will remove biases and treat this again. It's a mathematical modeling problem. There's a great effort of some of my colleagues in theory of computation, Omer Reingold, Cynthia Works, and many others with the social scientists and the policymakers to actually do that in a way that will influence both people and certainly the machines, the algorithms that are used more and more in support of judges and other decision makers. So it's a basic problem of defining it before you try to eradicate it and implement it.
And if I could add a little thing here,
Yes,
that the question of fairness goes beyond algorithms and computation. In order to know that something is fair, you need to understand the social context. It's not something that computer scientists or mathematicians can really solve by themselves. They have to work in collaboration with people in the social sciences or economics or fields that are relevant to the particular application and understand where there could be injustice and how the algorithms can be part of that scheme. And potentially can be part of the solution as well.
So Yoshua, this actually suggests to me that sometimes bias is desirable as opposed to undesirable, particularly in
humans have bias. As Avi said, we evolutionists put a lot of bias in the way that we make a lot of judgments. So there's probably a good reason for that, which doesn't mean we need to accept them without thinking about them.
It's not the same. Bias and unfairness are not equivalent.
So we are going to run out of time, and we also have to kind of close the session. We have 3 minutes left to do that. And so, Mr. Moderator, how do you want to proceed?
We have one quickfire question left. What do you suggest to a student who just joined their PhD?
My first reaction is figure out how to separate your problem from the rest of the universe so you can solve it and get your degree. I'll turn to my colleagues and ask them what's their advice. You have 30 seconds each.
There should be an advisor around there who can help.
Yann, what about you?
I'd say make an attempt at trying to solve a very ambitious problem, a very important one that is consequential. And then you will realize it's probably too hard, so you're going to renormalize your expectations and then maybe renormalize again. And then you'll find a sweet spot, which is something that is, just complex enough that you can do it within your PhD, but still an advance.
This is almost an Einsteinian observation. Problems should be hard, but no harder than you can solve them. Avi, what would you suggest?
Well, we discussed it before. I think you should definitely find out both what you like, where your passions are, and what you are good at, and those two are very correlated. So, go for this. What you are good, what you like will probably be what you are good at, and I agree. Try to be.
Alessio, you have the last word.
Yeah, well, I mean, it has been, I agree that follow the passion is the key for me. I think, as I said, it's the first encounter with real research. I think an advisor plays a crucial role also in guidance. So also listen to the advisor, try to, find guidance all along, because these are the critical years. And also one thing which is very useful that I sometimes, when I think back to the career, is that the more the career goes on, in reality, the less time we have as a researcher to just do research, because there are so many other things to do as well in our job. And so that's also the best moment to learn also. So also try, to read a lot of literature, see what has been done, and learn as many things as possible together. So this is really a great moment for growth. So I think the two things should come together. That would be also my advice.
That's a wonderful piece of advice. Enjoy your PhD. It will be the most fun time in your whole life, because you'll be too busy with everything else later on. And with that, we end the show, and thank every one of you for participating. Hope you have a great day. Bye-bye for now.
Thank you. Bye-bye.
Bye. Thank you.